Hello students, today we are going to start with the very important topic of the organic, okay, electronic displacements. And problem is that most of the students don't know the heading, okay, but they know the topics. Like when I say inductive effect, they will know. When I say electromeric effect, they know, okay. And some people are making mistakes. They are going only for the definition and example, so definition and example are not sufficient. What you will do, you will revise with the applications. Okay. So in this lecture, I will be giving you the applications also. Let's say effect increases what? Stability, acidic strength, dipole moment, lot of effects will be there. Bond length also affected. Okay. Hyperconjugation, and one more very important topic, SIR effect. Okay. Steric inhibition of resonance. So like that, lot of topics are covered. Now, the problem is that this lecture is going to be very lengthy. So you have to be very cautious about each and every point. Anywhere, if you feel that I am not able to maintain that interest, take 5 minutes break. Pause the video and take 5 minutes break. Okay. First of all, you should concentrate on the concept. Then after once you understood all the concept, then come back and take screenshots of the notes. Then you should make your own notes. Then that will be the best procedure. If any place you struck up, you are not able to understand, you can ask me in the comment section. Okay. This video is going to be very vital for your entire organic chemistry. Class 11th and class 12th, this is going to be very effective. Alcohols, aldehyde, carboxylic acid chapters are there in class 12th. Their mechanism you are going to understand from this lecture only. So you can read again and again whenever you get free time. This video will be very helpful. Sometimes after going through the some questions, again you revise this video, then it will be very useful. I hope all of you will take screenshots. First concept understanding, then taking the screenshot and then writing your notes. You take break in between, no problem, but attentiveness should not be lost till the last of the video. Okay. In the last, I have given some special key points, so don't miss that. See you. Start. Let's beginning. Okay, students. Now we are going to start with electron displacement effect. Okay. So there are plenty of topic, and every way, every time, every exam. Let it be from the state board examination, let it be board examination, let it be advanced examination. Definitely there will be one question from this. Okay. Electron displacement effect. And most of the students are not knowing the electron displacement effect word, but internally what types are there, they are knowing. Okay. So what are the types that we are going to see? Inductive effect, mesomeric effect, hyperconjugation effect, and electromeric effect. And other than this, we are going to study one more special condition that is called as a SIR effect. Okay. So that effect also we are going to study now, and lot of requirements are there in terms of the examination point of view. Okay, so just studying the inductive effect is not a use. Just studying mesomeric effect is not use. Just studying hyperconjugation. What will be the consequences of hyperconjugation effect? And by using the inductive effect, how you can check the acidic strength, basic strength. By using the hyperconjugation effect, how you can identify which alkane is stable, and why electromeric effect is temporary. Like that, so many interesting things we are going to discuss. Okay. So electron displacements are nothing but inductive effect, mesomeric effect, hyperconjugation effect, and electro, electromeric effect, and reverse hyperconjugation, SIR effect, lot of things we are going to study now. Okay. So let's start one by one. Now, first we will start with the very first beginning is inductive effect. Okay. So inductive effect. What is inductive effect? Definition. We will try to study in the two different ways. Okay. Direction, two different direction. Actually, inductive effect will be there in the polar nature of the covalent bond. It is attributed to inductive nature is attributed to polar nature. There will be partial positive, there will be partial negative due to unequal sharing of shared pair of electron. Okay. So the displacement of an electron, the displacement of an electron cloud along the carbon atom chain due to presence of an electron withdrawing group. Okay. Electron attracting group and electron releasing group. There are both ways. Some good person may give you electron, some bad person may take out the electron. In both conditions, you will get an effect that is called electron inductive effect. Okay. So electron, some books they write it as electron releasing, some places they write it as a electron repelling. Some books they write it as electron withdrawing, some place they write it as a electron attracting. But this withdrawing, releasing is mostly used. Okay. Now that carbon chain is known as inductive effect. Now I am going to explain here. So this is the very uniformly distributed electrons. Okay. So these are the electrons which are uniformly distributed. That means these two electrons are equally shared by the corresponding atoms. Okay. Now one fine day what happened? Some new group G is added to it. And once I say it is new group, definitely its electronegativity will not be just same as this carbon. So because of that, what happens? Electron will be either pulled towards group or electron will be released by the group. Both are chances are there. So let us say take this condition. So these two electrons, which are supposed to be exactly at the center of the carbon and group, they tend to be pulled by the more by the group and less by the carbon. So this electron will move in this direction. Okay. So because of that, it is losing, it is gaining. So what it will get? It will get partial positive and partial negative. Okay. Now once it is positive, then again these electrons will be attracted by this, but that it will not be that much effective as it is effective between this carbon and group. Okay. So the relative quantity of these two positive charge, which will be less, this will be less. Okay. Don't think that if I am writing 2 delta, that does not mean that it is double. It is less than the less. Okay. So delta means partial. Partial to partial means less than the less. Therefore, as the number of deltas increases, if number of deltas are increases, then what happens? Then the quantity of the charge will keep on decreases. Okay. So highest positive charge is not found in the last carbon, but found in the carbon which is directly attached to our group. Okay. So this charge will keep on decreasing, and after fourth carbon, it is assumed to be negligibly zero. It is assumed to be what? Negligibly zero. Okay. So this is what inductive effect. Okay. So I will try to explain in the other way. This also I tried. Okay. So let's see the other. Okay. Inductive effect may be defined as partial displacement of sigma bond pair due to dipole. Okay. Here which are affected? Sigma bond electron. This you will come to know the word importance when you study so many things. Okay. When you study so many things, then that time you will understand. Achha, it was sigma bond and somewhere it is something else. Okay. Now direct points. Okay. So some direct points I am going to tell you now, which will be directly reflected in the objectives. Okay. First, it can be defined as polarization. Inductive effect also due to polarization. That's why it is called as a polarization effect also. and it is also called transmission. We are transmitting, we are making the electrons to move, transfer, okay. And as it is a permanent polarization, it is also called as a permanent effect. The electron between the carbon and chlorine is permanently going to lie closer to the chlorine and away from the carbon. Then displacement electron takes place due to difference in electronegativity in the covalent bond. Suppose if it is carbon and here also it is carbon, then there is no chance of the inductive effect. Okay. There are two special conditions are there that I am going to cover in the forthcoming slides. Okay. Then electron never leave their original atomic orbital. It does not mean that it is not going to lie in the sp hybrid orbital or sp2. It is going to stay in the same orbital, but location is slightly shifted. Instead of exactly at the center, it will be more oriented, more nearby the more electronegative. So the magnitude decreases with the distance from the almost negligible after third carbon. That means from the fourth carbon. After the third and from the fourth, I spelled as a fourth carbon and here it is given as after third carbon. Okay. Inductive effect is always Inductive effect is always operating through the sigma bond, does not involve any pi bond. Okay. There is no permanent electron transfer of the pi bond electron. It is purely attributed to sigma bond electron only. It is purely attributed to sigma bond electron only. Okay. Now let's see the next one. Okay. So here this is the graph with diagram which I tried to draw, and here it is clearly drawn. Okay. Now let's see, it is a permanent effect which is transmitted along the carbon chain. This is the direction of transmission. That means the group which is we are thinking are attached is more electronegative. Okay. That also we will come to know what is the minus I, what is the plus I. The effect is insignificant beyond the third atom. Okay. So any atom or group which attracts electron more strongly than hydrogen, okay, exert electronegative effect, that is minus I effect. Whenever you will compare that electronegativity, some A is attached to our group. So whether that A is going to show positive inductive effect or negative inductive effect, we will compare with respect to hydrogen. If it is more electronegative than the hydrogen, it is going to show minus I effect. If it is showing less electronegativity than hydrogen, then it is going to show positive inductive effect. So inductive effect is a permanent sigma bond electron migration from less electronegative to more electronegative. Okay, and they are further divided into two types: minus I effect and plus I effect. Okay, is that clear now? Now let's see the next one. Okay, so group producing minus I. So which are the elements, which are the group of atoms which shows the minus I effect? Okay, first and very strong force is NO2. You will find so many questions in your aromatic especially. Okay, second will be cyanide, third will be sulfonate, aldehyde, carboxylic acid, fluoro, chloro, bromo, iodo. Okay, halogens, alcohol, ether, and amine. Triple bond, double bond, C6H5, and hydrogen. Okay, so highest minus I effect is shown by NO2. Lowest or negligible are reference from the hydrogen. Okay, reference from what? Hydrogen. Is it understood? Okay, now let's see the next effect. This is about the minus I effect. This is about what? Minus I effect. Now, special points you will remember. Okay, so there are some special category of the things which we should understand. Okay, what is that? Alkynyl. Okay, vinyl or phenyl groups are because of sp. Just now I told you, in forthcoming slides I will tell you, Even though carbon is attached to another carbon, that may show the inductive effect. That is just because of the difference in hybridization. Okay, sorry, difference in what? Hybridization. Okay, so if it is triple bonded sp hybridized, once hybridization changes, then electronegativity also changes. Electronegativity changes, electron transfer will takes place. Okay, so actually this complete s character, p character, so you need not to worry much about it. Simple, you will remember only two sentences. S character increases, electronegativity increases. S character decreases, electronegativity decreases. Okay. So this is what all about the special points. Okay. So whichever atom or group having electronegativity more than the carbon, they are all termed as a electron withdrawing groups. They are termed as what? Electron withdrawing groups. Okay. Okay, here alkynyl, vinyl, phenyl. They are having normal carbon if it is alkane. It is sp3 hybridized. In sp3 hybridized, total four orbitals are there. So S percentage character will be 25. So, but if it is sp, then only one s orbital 50%. In sp2, one out of the three, therefore 33 point. So, as the s percentage character increases, electronegativity increases, then it will cause the inductive effect. Okay. So, all such groups whose electronegativity is more than the hydrogen are called as electron withdrawing groups. What they are called as? Electron withdrawing group. Okay. So if otherwise they will be called as electron donating group. Okay, that will come to know in the next slide. So plus I group. Okay, so minus I group highest is NO2, second highest is CN. Similarly, if you cross check, very simple alkyl groups only. Okay, so it is 3 degree carbon. Understood? So this I will elaborately write so that you can clearly understand. Okay. Now to a carbon chain. So this carbon is going to attach to a carbon chain. This is further attached to three alkyl groups. Therefore, it can easily donate the electron. It can easily release the electron. So highest releasing the effect is shown by this group. Okay. And lowest as a reference only it is called as a hydrogen. Okay, lowest plus I group is hydrogen, highest plus I group is 3 degree carbon, then 2 degree, then 1 degree with bulky alkyl group, 1 degree with the methyl as a alkyl group. Okay, this is also 1 degree, this is also 1 degree, but that group attached is different. Understood? So this is about the plus I effect. Okay, now let's see the sum. This order you must remember. Okay, so next. Alkyl. Here you can see alkyl, cycloalkyl. They are also carbon atoms, only sp3 hybridized. So as I told you, inductive effect will be there only when there is a electronegativity difference is there. Now here electronegativity difference is due to dominance of the p percentage character. So P percentage character is 75% and whereas S percentage character is only 25%. P character dominates means donating dominates. S dominating means accepting dominates. S for accepting, P for the donating. So wherever P is dominating, which P orbital, okay. So electron releasing group or it is also called as electron donating group. That is the difference between the electron releasing and electron donating. Okay. If S percentage character increases, electronegativity increases, then S percentage minus A effect. P percentage character increases, electron releasing tendency increases, therefore plus A effect. That is what the gist of these two, these some important points. Okay. Now let's see the next one. Resonance or mesomeric effect. Plenty of questions will be there on the resonance. Okay, but direction of question, how they are asked and how you should write, that we will do in the objective session. Okay, we will do it in the objective session. So resonance effect, when a molecular ion can be represented by two or more structure. Normally, one molecule will have only one type of structure, but sometimes one type of molecule itself can exist in two designs or two structures. Okay, so like more structure which have same arrangement of atomic atoms position will not change, distribution of electron may be differed. Okay, that is called as a resonance. Understood? So like if I take an example of, let me take SO4 to 2 negative. Okay, in SO4 2 negative, see this can be written as oxygen negative, oxygen negative, double bond, and it is double bond. So this pi bond may be, lone pair may be pi bond and pi bond may be lone pair. Likewise, it can keep on migrating. That migrating structure itself, this we cannot say that negative charge will be always on these two oxygen. Some after some place it can be here, after some time it can be here also. So such structures where we have to draw two or more than two structures, then they are called as a resonance structure. They are called as what? Resonance structure. Okay. Like inductive effect got condition. What is that condition? There should be sigma bond and there should be electronegativity difference between the two bonded atoms. Okay. So resonance also will have some condition. Inductive effect only how many conditions? Two conditions. There should be sigma bond and there should be difference in electronegativity. Okay, and it is not mandatory that both atoms will be made up of two different kind, but sometimes it may be the same kind, but problem will be that electronegativity will be still difference due to difference in hybridization. So likewise, resonance also will be, a molecule can be shown in two or more than two structures. Okay. So two structures, what will be the difference? What is the condition for existence of resonance? Is first of all the conjugation. The main word reason for the resonance is conjugation. Okay. So given atom or group is said to be in conjugation with unsaturated system. Okay, unsaturated system means multiple bond. So directly linked to one of the atoms of multiple bond through a sigma bond. It has a pi bond, positive charge, negative charge, odd electron or lone pair. Okay, so these many types of conjugation are possible. First, let us see about the pi-pi conjugation. That means two pi bonds conjugation. See here it is pi bond. This is what available. Okay, and directly linked to one atom multiple through the single bond. Okay, so between the carbon atom, if they are sigma bond, then there are no chances. But there directly linked to one atom multiple bond through the single bond. Then there is a pi bond, positive charge, negative charge, odd electron and lone pair. Okay. So these are the some conjugations or conditions required for a molecule to show the resonance. Okay. What are the things? It should be directly connected to the multiple bonded carbon atom and it has a positive charge also. Okay. Pi bond also. Okay. Lone pair also. Okay, even free electron also okay, or negative charge. Okay, in this condition which part is taking place? See here, two pi bonds separated by a sigma bond. So then we can say that it is a conjugation, and this type of conjugation is called as a pi-pi conjugation. Okay, which conjugation? Pi pi, because carbon also pi or uh, carbon also belongs to the pi family. Okay, so this second bond, the carbon which is having second bond is pi family. Okay, and here this one also pi bond because double bond. Always in the double bond, one bond will be pi bond, another bond will be sigma bond. So two pi bonds are separated by one sigma bond. There should be at least one sigma bond through a single bond. Okay, next conjugation. This pi bond example we got it. Next is positive charge. Okay, so here pi bond with positive charge, pi bond and positive charge example. Next lone pair and CC, that is double bond, or we can say it is sometimes lone pair also possible. Okay, so here this carbon may have lone pair or chlorine may have lone pair. As the chlorine belongs to 17th group, it will use only one electron out of seven possible. So those remaining seven electron are can be utilized in migration of the pi bond. Okay, migration through the pi bond. Sorry, not by the pi bond. Then between the lone pair and C double bond C, between the odd electron and C double bond C. See, this is odd electron. Okay. Next, conjugation between negative charge. Okay. So first can be between two pi bonds, pi positive, pi negative, pi odd electron, and lone pair of electrons. Okay. Note down this. Then we will go further. Negative charge. Up to negative charge you can note down. Okay, this is about the conjugation types. Okay, after once they satisfy the conjugation, okay, there should be at least one conjugation, then there are resonance might be present, okay, but resonance might be present, still it will follow certain rules, okay, and most of the time there will be a question, which of the following are resonance structures, okay, so they may be identical, sorry, they may be have the same vital formula, but they may not be considered as a resonance structure until unless these following rules are followed. First of all canonical forms. Actually here, canonical forms means resonating structure only. And this is another way of pronouncing the resonance structure. Okay. All canonical forms or resonating structures must have proper Lewis structure. That is first basic. For instance, one of them may have a carbon atom with pi bond. That should not happen, okay? Because according to Lewis principle, it should have, carbon should have four electrons. So four will participate with four more electron, eight, okay? So here, see, if you count here, this carbon is having five bonds. So that means resonance problem will be there. Okay, this is not a proper resonating structure for methanol because carbon has five bonds. Okay, so the element in the second period or first major row of the periodic table cannot have more than 8 electron, their valence electron. So 8 electrons are maximum permitted. That is what it happens. Okay. So first thing is carbon should never form more than 4 bonds. In that 4 bonds also 2 sigma 2 pi okay, and all the 3 sigma bonds are okay. Okay. So that can be possible. But what is the main condition? Must have proper Lewis dot structure. Lewis dot structure means octet must be followed. Octet must be followed. Okay, after the condition Lewis dot structure is proper, then second condition, position of nuclei atoms of same in all structures. Okay, so you cannot change the position. If you are changing the position means they are not resonance structure. They will be called. They may be called as a isomer. Okay, so like here, 4 carbon atoms are there. Here also 4 carbon atoms. Okay, so this is not proper because structure 1 or 2 because of the hydrogen bond, hydrogen atoms are removed. Here hydrogen atoms are completely removed. Okay, so like positions 1 and 2, in order to form they would have move a hydrogen atoms, then that is not permitted. Okay, when you carefully observe, you will find there is a difference between the number of hydrogen atom on the given chains. Okay, first one is but1ene. First one is what? See here. This is pi bond double. This is also carbon positive double bond. Okay. So, but there is no such condition here. Third. Okay. So that's why it is not resonance structures. Number of atoms must be same as previously. Okay. Same as what previously. Okay, third condition, all atoms taking part in the delocalization must be in a plane, that is coplanar. Okay, so that they are parallel. See here, all carbons are sp hybridized, sorry, sp2 hybridized. Once sp2 hybridized, another p orbital will be perpendicular to the plane where carbon and remaining hydrogens are attached. Okay, and these two pi bonds. So suppose there are like this, how many will be there? 6 pi bonds will be there. Okay, so, sorry, sigma pi bond electrons will be there. Bonds will be only 3. So each 3 bonds will require 2 electron pairs. Okay, and once they lie in one plane, then only that sharing. Here the sharing is between the first and second carbon, and as these are also lie on the same plane, then the next transition next is becoming between the 2 and 3. Between what? 2 and 3. So first of all, proper resonating structure, proper Lewis dot structure. Second, number of atoms all must have same. Third one, all must be coplanar. Simple, at least like this way you can remember. Okay, next, fourth condition is all canonical forms. Canonical forms means nothing new. It is simple resonating structure only. Must have same number of unpaired electrons. Total number of electrons you can count unpaired. Unpaired means lone pair electron. Okay. So they must be same in all molecule. The energy of actual molecule is lower than any other form. That is called as a stabilizing phenomena. If somebody asks why resonance structures are stable, because during the resonance structures they are more stable due to complete delocalization. They, okay, is stabilizing phenomena. Then all canonical forms do not contribute equally to true molecule. Okay, time stable structure is greater than contributor resonating hybrid. Okay. So that means whichever is more stable, that means they will have the less energy. Less energy, more stable. Canonical forms do not contribute equally to the true molecule. Okay. Note down. Okay, resonance or mesomeric effect is just when a molecule or ion can be represented by two or more molecules. Okay, two or more structures which have same arrangement of atomic nuclei. You should not change the position of atomic nuclei, but distribution of electrons can be changed. You can keep the electron anywhere, but you should not change the position or linked with the atoms. If A is attached with the B, then it should be attached with B only in all structures. So then the various structures are called as resonating structures, and none of these truly represent. If you write three structures, actually all of the three are not confirmed, but they all will be present. Actual structure is the resonance hybrid of several contributing structures. Okay. So conjugation, the very condition for resonance is conjugation. Conjugation means a given atom or group is said to be in conjugation when in unsaturated, if directly linked to one of atoms of multiple bond through the single bond. So that means two double bond, between them there should be one single bond. Two triple bond, between them there should be one single bond, only one single bond. Okay. Two multiple bonds must be connected through a single bond. Otherwise, it may be connected with the pi bond also, it may be connected with positive charge also, it may be connected with the negative charge also, odd electron also, lone pair. But the main condition is that between them there should be one single bond. Between them there should be one single bond. Let's see in the first example. See, between two pi bonds, you will find a single bond. You will find a single bond here. Okay. In the second example, between positive charge and pi bond, there is a single bond. Okay. So like this, there should be a single bond between them. There should be a single bond between them. Like here, this is pi bond, this is pi bond. Between them, there is one sigma bond. This is positive charge, this is pi bond. And between them, there is a single bond. This is what conjugation. Until unless conjugation is not there, there is no chance of the resonance. Here, what is the conjugation? See, lone pair and pi bond. Between them, there is a sigma bond. Okay. And here conjugation is free electron and pi bond. Between them, there is a conjugation. And next example is for the between negative charge and here you will find a negative charge and you will find a pi bond. Between them there is a sigma bond. Okay. So there should be a multiple bond should be separated by a single bond or sigma bond with respect to it can be another pi bond. This is the example with respect to positive charge. This is the example with respect to lone pair. Okay, so this is the example of the lone pair, and this is the example of the negative charge, and this is the example of the odd electron. Okay, so these many types of conjugation are possible. They must be present, then only we can say that resonance will be existing. Resonance is simple. A molecule can be explained. A molecule can have two or more than two structure, but no one is perfect. If three structures are there, all the three are not perfect. By clubbing them, we will have one single structure, that is the actual structure. That is also imaginary structure, that is called resonance hybrid. Okay. So this is about the conjugation. Okay. This conjugation, how we are going to utilize it, that we are going to study in the next slide. Rules of the resonance. Canonical forms must have proper Levy structure. Their structure must be same. Next, position of atom should not change. Okay, you can change anything. You can change the electron position, but you should not change the position of atoms. Next, they should be in one plane, planar. They should have the planar so that the delocalization must takes place. Okay. Next, all canonical forms must have same number of unpaired electron. If two unpaired electrons are there, then everywhere it should be two unpaired electron may be there, but their position can change. Then the energy of actual molecule is lower than any form. That is the resonance hybrid. So that therefore delocalization is a stabilizing phenomena. So this factor we will be using more delocalization, more stabilization. Okay. So because stabilization consumes energy, therefore in the resultant molecule with the more stable delocalization will have the less energy, more stability. All canonical forms do not contribute equally. Suppose a resonance hybrid is made up of the four structures. So it does not mean that each contribution will be of 25%, 25%. Some may be more stable, maybe 70%, less stable, maybe 30%. Like that, that percentage will be depending on the stability. Okay. Next, see how to compare the stability. First thing, the structure in which all atoms have complete valency shell, that is octet. So if all having octet, then that is the best structure. Here, in this, oxygen also having octet, carbon is also having octet in the second structure. In the which structure? Second structure. So here octet is possessed by oxygen as well as carbon. But here problem is with the C plus. It has only 6 electrons. Therefore, this is more stable than the first one. This is the first and foremost rule for comparing the stability. Now let's see the next rule. Non-polar or uncharged are more stable. Sometimes all are having octet, but there is no problem. But still, see, this molecule does not have any charge. Okay, and here charge is there. So in that condition, non-polar or uncharged is more stable. So that's why, like in CO2, okay, we can write CO2 like this also. We can write CO2 like this also. Here both are same only, and both are having octet also. But this is more stable. Any resonating structure, if it contains without any charges, then that is considered to be more stable. But if there is charge, okay, the charge separation decreases the stability. Separating the opposite charges requires energy. Why we are saying it is unstable? Because it is very difficult to keep them away. Opposite charges will always attract with each other, and for keeping them away it require energy. So greater energy, lower will be stability. So therefore they do not have no charge separation are considered to be more stable. This is the reason behind the stability of the non-charged structure. Okay. Next, let us see if charges are there. Okay, structures with more covalent bond. Okay, so here it can be sigma bond or pi bond, not a problem. The electron must lie in the bonds rather than in the charge. Rather than in the charge. Here total number of electrons, total number of sigma are same. But in this structure, what you will find, the electrons are lying in the bonds. But here you are finding that electrons are in the lone pair. Here you find that electrons are in the lone pair. Therefore, number of electrons which are more in the sigma or pi bonds is considered to be more stable. This is the more stable. Okay, this is somewhat similar to previous one only, but slight modification. Next, the structure that carry negative charge on most electronegative and positive charge on less electronegative are comparatively stable. Here we have two atoms, carbon and oxygen. Oxygen is more electronegative. In whichever the structure negative on oxygen, and positive on carbon will be stable. So here negative charge is on the carbon, so it is unstable. Here negative charge is on the oxygen, more stable. Okay. So if charge is must, then what we will do, we will try to accommodate the negative charge on the most electronegative and positive charge on the less electronegative. Okay. So these are the some rules. Maximum number of bonds must be there. Charge should be avoided. Okay. Charge separation requires energy. Understood? And neutral molecule is more stable. If charges are there, we should try to accommodate in the most electronegative. Should have the negative charge, less electronegative should have the positive charge. As no energy, there is no orbital, there is no resonating structure is complete. Okay. So therefore, resonating hybrid will have the lowest possible energy. Then the difference between our each and every resonating structure with respect to resonating hybrid is called as a resonance energy. The stability of molecule directly proportional to resonance energy. So more gap between the resonating hybrid and resonating structure. Let us take this is resonating structure. This is the resonating hybrid. More gap, more will be the contribution in the actual structure. Okay, this is the diagram. So this 36 kilocalories is the difference between the, this is resonating structure. Okay, this is resonating hybrid. So their difference is same. Their both difference is same. That means 50-50% contribution. So if the resonance energy between two resonating structures are same, then their contribution also will be same. Like benzene thing, this is one, this is one. So both will exist 50-50%. Like in ortho, meta, para that we'll study in aromatic structures, there you will come to know. Somewhere we will write major product, somewhere we will write minor product. Major product means their contribution is more. Contribution is more means that energy between separation between that particular resonating structure and its own resonating hybrid is more. Once more difference, what does it mean? Their contribution will be more. Contribution will be more. Okay. Now let's see the next one. Types of resonance are mesomeric effect. So electron can come into the ring or into the conjugation system. Electron can go away from the conjugation system. So when movement of electron from particular group towards the carbon chain, that is conjugation. Okay. See, this is a group, particular group. Okay, and electrons are moving into the carbon chain. That means electrons are added. Added means plus M. Okay. So this is how you will remember. Any group which adds electron to the conjugation system or to the carbon chain, then that effect is called as a plus M effect or plus R effect. Okay. It takes place when it is possible. It should have the lone pair to donate or lone pair to pump in inside the resonating structure conjugated, okay, or at least some extra electron. So the best way to find out is any group with lone pair. If it is having lone pair, that means it is going to pump in the electrons in the form of the pi bond into the carbon chain. Okay, so examples amine. In amine, you will find lone pair on the nitrogen. Alcohol, lone pair on oxygen. Three lone pair on the halogen in the Cl, and alkoxy lone pair. Whichever group is having lone pair, that is supposed to show mesomeric effect of addition, that is plus M effect. Okay. Now let's see the next effect, what it is possible. See, this is how which explains about the orthopara. Orthopara tendency of the chlorine. See, chlorine is a plus M group. Okay, plus M group because it is having lone pair. Now, during the structure, see, electron density is maximum. I think all of already you are aware. This position is called ortho. This position is called meta. This position para. Then again meta, and this position is ortho. This we have discussed in the isomerism. Okay, isomerism, position isomerism we have discussed. Okay, so here where you found electron density maximum, ortho. See, in the next position, you are not having electrons at the meta position. Again, it will be para. Okay. Then again ortho. That means electrons are found maximum at ortho and para. Okay. That's why chlorine due because of the lone pair. It is plus M group. Okay. And plus M group when suppose any reagent comes, it will prefer to attach itself at ortho position or at para position. That's why this is called as a OP directing or directing OP directing. That means when on a benzene ring, if already chlorine is there, then the next group will prefer to attach itself at the ortho and para position. So all plus M groups. This is example with respect to chlorine I have taken, but you can apply it to all plus M group like amine, alcohol, alkoxy. All plus M groups are OP directing, and because of them electron density on the benzene ring is increasing. Because of them electron density on the benzene ring, what happens? Increases. Okay, these are the two things you will remember. Mesomeric effect, if it is plus M, electron density increases and the next coming group will be attached itself on the ortho para position because of its more electron density at that particular position. Okay. Now let's see the next slide. So not everybody will give the electron to the conjugation system. Somebody will take the electrons from the conjugated system also, or carbon chain. So this group is taking the electron away from our conjugated system, or taking the electron from the benzene. That groups are nitro group. Okay. So these people think that this is ketone. No, it is. It can be ketone, it can be aldehyde, it can be acid, and then it can be nitrile, it can be sulfonic acid. Okay. So in general, how to identify, how many examples you will remember, that is a memory trick. Okay. So memory trick is that in general group showing having attached atom unsaturated with more electronegative. See, this is unsaturated. Why unsaturated? Because pi bond is there. And out of these two, this is more electronegative. Okay. So more electronegative, this is going to attach on the benzene ring. The atom which is attached to the benzene ring will have the pi bond, and that pi bond also will be with the more electronegative. Like nitrogen is attached to benzene ring and it is attached with the oxygen with pi bond. Same way sulfonate. Okay. So here this sulfur is going to attach with the benzene ring. It is unsaturated because here pi bonds are there. And that pi bond is with the more electronegative oxygen. More electronegative oxygen. That is the trick. You need not to now memorize which are plus M, which are minus M. Okay. So lone pair is there plus M. Pi bond with more electronegative is there minus M. Okay. There are some exceptions that we will come to know. Okay, next, this is how meta directing. Okay, minus M groups are meta directing. Why? That is also because of the ortho para only. See, electrons are taken away by the nitrogen. Okay, this from the conjugated system it is taking. So electron density decreased at ortho position, and here electron density decreased at para position, electron density decreased at ortho position. That means group whichever it is coming, it never wanted to come at ortho and para because already electrons are less over there. So somewhat okay position is what? Meta. Somewhat okay position is what? Meta, because you will never find electron density decreased at meta position. Therefore, group itself will attach at the meta position. That is the first thing. Minus M groups are which directing? Meta directing. Meta directing. Okay. and because of them electron density decreases. Electron density what happens? Decreases. Plus M, electron density increases and orthopara directing. Minus M, electron density decreases and meta directing. Okay. And one more thing, the shortcut, lone pair plus M and pi bond with more electronegative minus M. I think it is clear now, 3 points. Now let's see the next, hyperconjugation. Okay, so we have studied inductive effect, we have studied resonance or mesomeric effect. Now we are going to study the third effect. Okay, and we have SIR effect also. SIR effect. What is that SIR effect that we'll study? So try to be attentive till last. Okay. So now hyperconjugation effect. This is also called as Baker-Nathan effect. Okay, because he observed that alkyl groups, this is alkyl groups with at least one hydrogen at the alpha position, alpha carbon. Okay, so there should, alpha carbon means active carbon. Let us take, this is active carbon. Any carbon attached to alpha carbon, sorry, active carbon is called as a alpha carbon. This is active carbon. Active carbon means it can have functional group, it can have pi bond, it can have positive charge. So this is highly reactive carbon. Any carbon attached to active carbon are called as a alpha carbon, and any hydrogen available on the alpha carbon are called as a alpha hydrogen. Okay. Now, unsaturated carbon atom. So, what is active carbon? See, first it can be unsaturated hydrocarbon, that is pi bond, or it can be positively charged carbon atom. It can be odd electron carbon atom. Okay, able to release electron quite similar to that of electromeric effect. Okay, so it is ready to, actually there is no conjugation here. In the mesomeric effect or resonance effect, conjugation is must. See, you don't find any conjugation. But this is the active carbon, okay? This is the alpha carbon and this is the alpha hydrogen. So here this sigma bond is converted to pi bond, okay? So that unique capability lies only in the alpha hydrogen. Normally you will find atoms converting their pi bond into sigma bond, but here you will find sigma bond converted to pi bond. So that effect is called as a hyperconjugation. There is very important 2 points you will remember. This is possible only when alpha hydrogens are there. What are alpha hydrogens? Which are connected to alpha carbon. What are alpha carbon? The carbon which is directly connected to active carbon. What are active carbon? Carbon with the pi bond, carbon with the positive charge, carbon with free electron. Okay, so they are called active carbon. Okay, second thing, during the hyperconjugation, dash bond is converted to dash bond. Sigma bond is converted to pi bond. Which sigma bond? The sigma bond between alpha carbon and alpha hydrogen is converted to pi bond. Is converted to what? Pi bond. Okay. Now let us see the next example. Okay, the type of electron released by type of electron released by alkyl group is called hyperconjugation. Okay, it involves delocalization of sigma and pi bonds. That's why this is called as a sigma pi conjugation. What it is called as? Sigma pi conjugation. Okay, so in the structure too, that no, there is a no definite bond between the carbon and hydrogen. Therefore, it is called as a no bond resonance. What is that? That we are going to see now. See here. It is just hanging. Okay. So here, just I will point out this. See, this hydrogen, this carbon, there is no bond between them. So that's why this is called as a no bond resonance. What it is called as? No bond resonance. What are the names we gave? Baker-Nathan effect, hyperconjugation effect, and sigma pi conjugation, and no bond resonance. Okay, these are the names given to which effect, hyperconjugation effect, other than them. Okay, so now very important questions are not in the form of the definition, they are in the form of the applications. Okay, so before going applications you should know that some basic points. Greater the number of carbon and hydrogen, alpha carbon to the unsaturated system, greater will be electron release and greater will be hyperconjugation effect. Greater will be which effect? Hyperconjugation effect. Okay. So again, greater hyperconjugation, greater delocalization, greater will be stability. Okay. Hence, electron release due to presence of 3 alpha is in the methyl group is greater. Okay. See here, 3 alpha hydrogens are there. People think that in ethyl, more hydrogens are there, more will be the hyperconjugation. No, you should consider only alpha carbon. Don't consider this. Okay. So here, how many alpha hydrogens are there? Only 2. Here, alpha hydrogens are here, how many? 3. And here this is the alpha carbon. So it is having only one alpha hydrogen. It does not have at all. Okay. So no alpha hydrogens. That therefore don't go for the bulkiness of the group. Go for the number of hydrogen directly connected to the alpha carbon. Okay. So that is how you will remember. Is it understood? So ethyl group is less hyperconjugation than the methyl group. That is because of the number of alpha carbon. That is because of what? Number of alpha carbon. Okay. Now let us see the next one. So more alpha carbon, more will be hyperconjugation. That's why when you have to arrange the alkenes in the increasing order of their stability. Okay. So hyperconjugation explains the order of stability of alkenes double bond. Suppose propene more stable than ethene because in propene, see this is a propene. Okay. So 3 carbons are there. Now third carbon atom will be alpha carbon and these hydrogens will be alpha hydrogens. Okay. So, but in ethene, you don't find alpha carbon itself. Okay. So, active carbon, both are which carbon? Active carbon, active carbon. So, there is no third carbon atom which can be called as a alpha carbon. That's why propene is more stable than ethene. I think it is clear now. Hence, greater number of methyl, greater will be the alpha hydrogens, then more will be the stable, more will be the stability. Okay, so if more structures are given, this is very simple question. Okay, so sometimes they may increase the number of like this. Okay, so here main problem people students are facing is identifying the alpha carbon and identifying the alpha hydrogen. See, first point out the active carbon, these are the active carbon. Then what you will do, point out the carbon atom which is directly attached. This is active, there is no carbon. So this is alpha, this is alpha carbon. Sorry, this, okay. And 3 alpha hydrogens on this, 3 alpha hydrogens on this. Therefore, 6 alpha hydrogens. Okay. So active carbon, alpha carbon, alpha carbon. Okay. Now both are having 6 alpha hydrogen. Okay. Now then what you will do, more carbon hydrogen bond on the same carbon, greater effect. Here this carbon is having 6 alpha, but here 3 alpha here. So therefore this will be more stable. Okay. This principle applicable only when both of them have same number of alpha hydrogens. Okay. Then here it will have 3 alpha hydrogens, obviously less. Okay. Now next one, no alpha hydrogen atom. Here there is no use at all. Alpha carbon, this is active carbon, this is active carbon, this is alpha carbon, but no alpha hydrogen at all. Therefore, it is least stable. Here one alpha hydrogen, here two alpha hydrogen, here all alpha hydrogens. Okay. So identifying alpha hydrogen is now I think clear. Okay. So more alpha hydrogens, more will be stability. Okay. Less will be reactivity. less will be reactivity. Okay, then already I told you again, just intimation, the presence of at least one hydrogen, that is alpha hydrogen is must, okay, which is alpha with respect to alkene, alkyne or carbocation, free radical, benzene nucleus, okay. So let us say take some examples. Hyperconjugation in alkene, double bond. Okay. So delocalization of sigma bond in pi orbital by hyperconjugation is depicted as below. Okay. So actually there was a pi bond. This is a pi bond. Okay. Now this is alpha carbon. Okay. So during this alpha carbon there will be sigma bond converted to pi bond. This pi bond electron will go to the lone pair. See here, there is a bond in this structure, but there is no bond here. There is a pi bond here, though, but now it is converted to lone pair. Okay, this is orbital diagram. This is skeleton diagram regarding the alpha hydrogen and hyperconjugation. Okay, next. Hyperconjugation, that is in alkenes. Now the next example is hyperconjugation in carbocation. Here active carbon is this one because of its positive charge. Now this is the alpha carbon. Okay. Now these are the two electrons shared by the hydrogen and carbon. Now this will come over here. Okay. So this will result in a structure like this. Pi bond will be there and now this will be neutral. Earlier this was carbocation. Now it is converted to neutral. Then this positive charge is ultimately shifted on to the hydrogen, H positive. Okay. Then hyperconjugation in free radical. This is free radical. Now you should be very careful. Here half arrow means one electron. Full arrow means two electrons. Okay. So this electron will remain as it is, okay, because this bond is shifting from here to here, so only this electron is transferred to this carbon. That's why we use a simple half arrow, and this hydrogen is hanging hydrogen. Okay, so three types of hyperconjugation we have studied: hyperconjugation in alkenes, then hyperconjugation in carbocation, hyperconjugation in free radical. Okay. Next, hyperconjugation in toluene. Okay, now I told you in the resonance there are some exceptions. Exceptions in the organic does not mean that it does not have the explanation. Okay, explanation is there. Now people ask, sir, you said lone pair is there plus M. Okay, plus M will increase the electron density increases. Okay, electron density increases, ortho para directing. Okay, pi bond is there. Pi bond will be minus M. Electron density decreased. Okay, so then it will be meta directing. That is good. But why toluene is ortho para directing? Okay, so that is explained on the basis of hyperconjugation. See, toluene is not having pi bond, therefore it cannot be meta-directing. Or toluene is not having lone pair, it cannot be orthopara-directing. But it is orthopara-directing. Why? Because of the hyperconjugation. So this is the active carbon, this is the alpha carbon. Okay. Alpha carbon is attached with how many hydrogens? Three hydrogens. That means toluene have three alpha hydrogens. Okay. So if somebody asks that ethyl benzene and methyl benzene, okay, are ethyl benzene and toluene, which is more stable, okay. If question is ethyl benzene and methyl benzene, which is more stable? Which is more stable? Okay, ethyl benzene is having only two alpha hydrogen. Toluene have the three alpha hydrogens. That's why this is more electron releasing group than the ethyl benzene. So this exception and explanation. Why toluene is orthopara directing? Due to hyperconjugation. Okay, in the hyperconjugation, sigma electrons between the alpha carbon methyl group carbon and hydrogens are transferred as a pi bond. Therefore, it will increase the electron density as usual at ortho and para position. Therefore, it is more stable. Okay, and electron releasing means it is electron density increases at ortho para position. Therefore, it is OP directing. Toluene is a OP directing. Okay, now let's see the next one. We have seen hyperconjugation in alkenes. We have seen hyperconjugation in carbocation. We have seen hyperconjugation in toluene. Okay, now let's see the further examples. Heat of hydrogenation. First, we have studied about the stability. Okay, which is more stable? How we will understand? We will understand with the help of the alpha carbon. Second application of hyperconjugation is heat of hydrogenation. Very, very important. Greater the number of alpha hydrogens, greater the stability. Therefore, greater the extent of results over lower value of hydrogenation. Already it is stable. Okay. See, this is having active carbon, alpha carbon, alpha carbon. So it is having 6 alpha hydrogens. This is active carbon, this is active carbon. There is no alpha. So here alpha is there. So 3 alpha hydrogens. Here only active carbons are there, no alpha carbons. Therefore, 0 alpha hydrogens. So whichever is having more alpha carbons and more alpha hydrogens will have the least, see this is the symbol, okay, will have the least heat of hydrogenation. You will find more heat released during hydrogen added to the ethene rather than butene. Okay, this is another application. But major application will be in the stability only. Okay, major application will be in the stability. Okay, and somewhat some more applications are there in the bond length. Okay, so actually whenever it is attached to the this carbon carbon bond length I am talking about. Okay, so here it is single bond, but its bond is not exactly as a single bond because hyperconjugation after some time it is double bond character. This is called as a PDC, partial double bond character. Okay. So if this resonance is not there, then this will be always sigma bond or single bond. So, but because of the hyperconjugation, sometimes it gets chance to become as a pi bond. Okay. Therefore, the bond length of carbon 2 and carbon 3 is less than the normal carbon-carbon single bond because it is single bond. After some time it is double bond. Even carbon 2 and carbon 1, see carbon 2 and carbon 1, it is double bond, but it is more than the double bond because after some time it is becoming as a single bond. Okay, and carbon hydrogen bond is longer than the normal carbon hydrogen because now there is a single bond, but after that there won't be any single bond. Okay, so that is the bond length variation. That is also explained in terms of what? Hyperconjugation only. Okay, so this is the next example. See, this chlorine is attached to the alpha active carbon. Okay. Now, here, when it is attached with the aldehyde group. Okay. Now, carbon chlorine bond length. We are talking about the carbon chlorine bond length. In one is greater than the two. Okay. Because of this is hyperconjugation. This will spread all over this. Okay. So because of that, what happens? There will be hyperconjugation. This bond will be shifted here, positive charge. Therefore, carbon chlorine bond length in one. There is no group to disturb this bond length. Okay. Therefore, in carbon chlorine bond length of first is greater than the second. Okay. So these are the some applications of hyperconjugation. Okay. Now, misconcepts while counting the I have seen some people are giving the wrong answer during the classes. So I have collected the misconcepts by the students. Okay. First, if any group has more than one pi bond, like here three pi bonds are there, sorry, two pi bonds are there, but only one pi bond will take place in the delocalization. Okay. Here I am talking about this carbon and carbon. Sigma bond is okay, but this pi bond. So if anybody asks how many electrons can be delocalized, but electrons delocalizable are four. But at a time, either these two will be delocalized or these two will be delocalized. So out of the two pi bonds, only one pi bond will take part in delocalization at a time. Okay. So suppose if it is delocalized, then after some time it can delocalize, but at the same time, both pi bond will not be delocalized. Okay. Second thing, in any conjugate position, more than one lone pair. Same problem with here also. Okay. Here this is having two lone pair, but out of them only one will participate in conjugation at a time. So these either these two will participate or these two, but not both. Okay. So out of the two lone pair, only one will participate in the delocalization. Okay. Second misconcept is now clear now. Okay, next. Third, also very dangerous misconcept. In any conjugate position, as a pi bond and positive charge, negative charge, odd electron, lone pair, the only pi bond will take place in the delocalization as a priority. See here, these two are in conjugation, these two are in conjugation. So, but preference is given to what? Pi bond only. Nitrogen has a pi bond as well as lone pair, but pi bond of the nitrogen will takes place in the delocalization. Okay. So this delocalization is much more effective than this lone pair. Okay. So two lone pairs are there, only one lone pair you will count. Two pi bonds are there, only one pi bond you will count. If pi bond, lone pair both are there, you will count only pi bond. Okay. Then electrons of the negative charge or lone pair behaves as a 2 pi electron. This is very important in the Huckel rules, resonating structures. What do you call? Aromaticity. Aromaticity we will count that time when 4n plus 2 rule will come. Okay. So there it will be misconcept used, but roots are there in the resonance. That's why here only I am covering. Okay. So if they ask number of pi electron in this one, okay. So people will say 2 pi bond, therefore 4 electron. No. Here now it is lone pair, but after that this will be converted to pi bond. This will be converted to lone pair. So any lone pair, and again also again and again telling here one more lone pair also there, but you will count only one lone pair in the conjugation. Okay. So don't count this one. So this lone pair also should be counted. So n value is how much here? 3. Two pi bond and one lone pair. So three lone pairs are in the conjugation. Same is here, one pi bond lone pair. So two pi electrons. Okay, here also two pi electrons. Here three pi electrons. Okay, these two lone pair electrons. If these are not there, then they are not counted as a pi bond. Okay. Okay, next electromeric effect. What is the next topic? Electromeric effect. Okay. As of now, whatever the we have studied, hyperconjugation, resonance, inductive effect, they are all permanent effects. They are all permanent effect, but electromeric effect is a temporary effect. Temporary means it will takes place only a certain condition. Okay. Operates only in a molecule having pi electron induced by attacking reagent. It will work only in presence of reagents. Okay. Reagents are how many types? Two types, electrophile and nucleophile. So they are there in the definition itself. Nucleophile, nucleus attracting. electrophile, electron attracting. Suppose positive charge is there, positive ion, that will attract the electron. Okay, so that's why that is called as electrophile. If anybody have negative charge, that will attract the positive nucleus. Therefore, it is called as a nucleophile. So, for electromeric effect to takes place, what are must? Attacking reagent must and pi electrons also must. Okay. So, in presence of electrophile, pi electron shift to other carbon, make adjustment to the incoming electrophile to be added. Okay. Suppose this is a pi bond. Okay. Now electrophile is approaching. Electrophile means this positive. Okay. So now what happens? This electron will shift here. That I through the diagram I will again explain. So this will be negative. This will be positive. Now this will be accommodated over here. Okay. So in presence of electrophile, pi electron shift to other carbon atom to make adjustment for the electrophile to be added. Okay. So condition for electromeric effect, the presence of reagent and presence of pi bond. Okay. See electromeric effect. This is what I have explained through the diagram. In presence of electrophile, electron shifted here. This is negative, this is positive. So positive will attach itself. Okay. So here ultimately we can say this positive charge which was there on the electrophile is added to this carbon. Okay. So we observe that electrophile adds to the group whereas electron transferred. Okay. Electrons also given to this carbon, group also attached to the same carbon. Such effect is called as a plus E effect. What it is called as? Plus E effect. That means attacking reagent electron transfer. If takes place on the same carbon, then it is called as a plus E effect. It is called as what? Plus E effect. Opposite will be the minus E effect. What is that? We will come to know now. Okay, minus E effect. Here it will takes place in the case of the that was electrophile and here it will be nucleophile. Okay, in polar bonds in presence of attacking reagent, complete transfer of electron. Okay, to the more electronegative atom takes place in presence of nucleophile. See here, electrons are given to oxygen, but our CN attached to carbon. Okay, so both are taking place on the adjacent. Okay, not on the same. In the previous condition, we have seen that both are taking place on the same atom. Okay, so then it is called minus E. If an adjacent, then it is called plus E. Okay, so here that takes place in electrophile. This takes place in nucleophile. Okay. That is called minus E effect. Okay, now next application. Next application is stability of reaction intermediate. Here we are going to study all together stability of reaction intermediate. Okay, so reaction intermediates are divided into few types like carbocation. Carbocation means positive charge on the carbon. Here, reaction intermediate. What is reaction intermediate? That we are going to study separately. So, carbon with positive charge, that is called as a carbocation. Okay. Now, in carbocation will contain only 6 electrons. Will contain only 6 electrons. So because of the only 6 electrons present on the carbocation, there must be electrons must be pumped into carbon so that this electron deficiency can be fulfilled. Therefore, on this carbocation, if anything is there like plus M group means electron should be released or anything plus H, hyperconjugation group, plus I group, plus inductive effect group. Okay. So So any of these group present on the carbocation will improve the stability, improve its stability. Okay, what is the reason? I think it is clear now. Due to the presence of less electron, it is having only 6 electron. Carbon have 4 electron. Because of the positive charge, it lost one more electron and 3 electrons are only left over. So there will be only 6 electrons. Out of the 6 electrons, to it will destabilize it because octet is not yet obtained. So that can be compensated with a plus. Okay. Then carbon free radical. Same problem with the carbon free radical also. Free radical means it have to keep the one electron free. Okay. So even though it have 4 electron, free radical, that means one electron must be free. So again, there will be 7 electrons in this one because one electron is not allowed to participate in the bond formation. Again, plus groups only will help out. Understood? Then carboanion. So anion, carbanion, that means it will be negative charge. So because of the negative charge, there will be lone pair. Now it is electron rich. Wherever lone pair is present, that means it is electron rich. So this must be eliminated. This must be utilized somewhere else. Therefore, minus group will be helpful in improving the stability. Okay. Carbocation plus groups plus effect, that is plus MEffect plus H effect plus I effect. Whereas free radical only plus I effect, and stability of carbanion will be improved when minus M effect and minus I groups are attached. Okay, this is about the stability on applications of electron displacement effect. Okay, now let's see the next one. Okay, these are the some another example of dipole moment. Okay, dipole moment also affected by reaction intermediates only. Okay, so dipole moment means electron moving towards the one of the atom. So since hyperconjugation causes development of the charge, in this is what is happening, carbon and carbon. This is, let us take active carbon. So whatever the carbon which is attached to the active carbon will be changing its sigma bond into the pi bond. Sorry, not this one. This, okay. So this will be shifted here. Now because of this, this pi bond will be shifted here. There will be charges will be generated. So wherever charge is generated, it is going to affect the dipole moment. Dipole moment will be affected. Okay. So let us take, there is no dipole moment in the ethene. Why it is not available? Because of the lack of the alpha carbon itself. Now here this is active carbon, this is active carbon. So this is alpha carbon. This is alpha carbon. So electrons will migrate in this direction. Dipole moment will be generated. Therefore, wherever hyperconjugation effect is present, there what happens? Dipole moment will be increasing. Now let us take, this is the high active carbon. There is no active hydrogen, alpha carbon, alpha hydrogens are not available. Here this is active carbon and this is alpha carbon. So 3 alpha hydrogens are there. Same way here, number of active carbons have increased. So number of alpha hydrogens migration will also increase. Therefore, this will also cause the dipole moment. Okay. Next, more number of dipole moments. See here, this is negative, and this is COH and this is COH. Okay. So, but this will be because of this hydrogen, there will be plus and minus. There will be plus and minus. Okay. So, there will be dipole moment will be there. Understood? Now, let us take the next example. Nitro group, toluene group. Here, this is minus I group and minus M group, and this will increase its charge by releasing the electron. This will show the plus H, okay, hyperconjugation. and there is no plus H group over here. Okay. So because of the methyl group which will show the hyperconjugation, this dipole movement have increased. Same case with the phenol and phenol. And there is no hyperconjugation, but there is a hyperconjugation because of the methyl group. Okay. Ultimately, wherever there is a alpha carbon and alpha hydrogen, it will cause the uh, hyperconjugation effect, and hyperconjugation effect in turn what it will do, it will increase the dipole moment. Okay, this is the next effect of the dipole hyperconjugation. Okay, next, acidic and basic strength. Definitely there will be a question according to the acidic and basic strength of organic compound, stability and acidic basic strength. Most of the questions are based upon these topics only. Okay. Acidic strength increases when minus I and minus M. Wherever minus I and minus I groups are there, they will increase the acidic strength. Same way, basic strength increases when plus M and plus H and plus I. Plus M, plus H and plus A groups are available, and solvation effect. Solvation means hydration only. Okay. In case of the water, it is called solvation. Other than anything, it is solvation effect. Okay. So simply you will remember minus will increase the acidic strength, plus will increase the basic strength. Okay. So how it is that we are going to do in the questions. Okay, next, very important for the advanced examination, SIR effect. Okay, SIR effect means steric inhibition of resonance. SIR means steric inhibition of resonance. So restriction in exhibition of resonance. See, inhibit means stopping. Okay, what is stopped? Resonance. Because of what it is stopped? Steric. Okay, steric means absence of place. So due to steric hindrance, resonance cannot be exhibited. Due to steric hindrance, resonance cannot be exhibited. So that effect is called as a steric inhibition effect of resonance effect or SIR effect. Okay. So this will happen in case of the 1,2-disubstituted benzene. 1,2-disubstituted benzene means suppose this is the benzene. Now this will be 1. So this will be 2, this will be 2. So when bulky groups are available here, bulky groups are available here, then this group will be unable to show the resonance. Okay, because the group without the plane with respect to the benzene ring, out of the plane with respect to benzene ring. Okay, so out of the plane means suppose there is a carboxylic acid. Okay, so in the carboxylic acid it must be in the same plane, they all must be in same plane, but bulky group what it will do, it will flip. Okay, it will rotate. See here, I will show. Suppose this is a benzene ring. Okay. And if no groups are there at the second carbon, then COH group will be parallel. Okay. So, but here two bulky groups are there, then it will flip out, ring out. Okay. This is the benzene ring, then this will be the carboxylic group. But basic requirement for resonance is coplanar. For showing the resonance, what is the requirement? There should be coplanar. In the plane it should be there. So because of the bulky groups on the second position with respect to our functional group, this functional group will go perpendicular to the benzene plane. So once it is out of the plane, what will happen? If it is out of the plane, then it cannot show the resonance, because resonance condition is that there should be molecule must be planar, okay, coplanar. Next, due to this change in planarity, conjugation between the substituent and the benzene ring slightly diminished. Therefore, that is what called as a SIR effect. Okay. Now, SIR effect is directly proportional to size of the group. The more bulky it is, the more rotation will be there. So more it will be out of the plane. So more will be the SIR effect. Okay. So this is about the SIR effects. Because of the SIR effect, resonance cannot be shown. What is the reason? Due to the steric hindrance. Due to steric hindrance provided by the group attached on the second position with respect to the functional group, it is unable to show the resonance effect. That is what called as a SIR effect. Okay. So examples are this one. SIR effect. Okay, bulkiness we have to see. What we have to see? Bulkiness. So in the first example, you can see COH is affected. Who is affected? COH group is affected. Okay. Now, COH group is affected due to the stericness of the methyl group, ethyl group. These groups are showing the stericness. Okay. So here highest stericness is shown by the group 3. Okay. So that's why see steric hindrance is maximum here. Second is largest will be this one. So this is the second. And the say here then propyl, ethyl and methyl. Okay, steric hindrance is directly proportional to size. So SIR effect is maximum in the 3. That means there is no chances, less chances of resonance in the first one. Okay. Now let us see the next one. Here this is a fluorine, chlorine, bromine and iodine. So bulky group is iodine, then bromine, then chlorine, then fluorine. Okay. This is the SIR effect order. What is the SIR effect? I think it is clear now. Okay. So if you got any doubt, you can ask and let us solve some questions related to it. Okay.